Imagine this scenario. You have spent hours building an application on your laptop. Everything works perfectly. You smile and say, done. It works on my system. But the moment you send to production, it crashes, dependencies fail, configuration errors appear everywhere. And suddenly you are stuck, thinking that, but if worked perfectly on my machine, why it is failing now? Now let me explain this in a real world way so you never forget it. Think of this as a restaurant. A developer is like a chef cooking a dish at home. At home, the kitchen setup is perfect. Small utensils, small ingredients, same environment. Now at the restaurant, which is a completely different kitchen, different tools, different ingredients, different setup. So when the chef tries to cook the same dish there, the taste changes or sometimes it completely fails. Now Docker solves exactly this problem. Docker says, let's pack the kitchen along with the recipe. So wherever you go, home kitchen, restaurant kitchen, or even cloud kitchen, the dish always stays the same. That packed kitchen is what we called a container. Docker is a tool that packages your applications along with everything it needs: code, libraries, dependencies, and even configuration into a single unit called a container. So your applications runs the same way everywhere. Whether it's a laptop, testing server, production cloud, no surprises, no failures due to environment differences. In today's session, we will understand what Docker really is, why containers are needed, and how Docker solves real-world deployment problems. Before we move ahead, if you are serious about building your career in cloud computing and DevOps, then here's something you should not ignore. Today, companies are not just hiring developers, they're hiring cloud engineers, DevOps engineers, platform engineers, and even AI-powered infrastructure specialists. And to become job-ready in this space, you need more than just theory. You need real-world skills, real projects, and industry recognition. That's exactly what this program offers. The IITM Pravartak AI-powered Cloud Computing and DevOps certification program, in collaboration with AWS and Microsoft, is designed to make you industry-ready. In this program, you will learn AWS, Azure, Google Cloud fundamentals, along with DevOps tools and automation pipelines, and also AI-powered cloud deployment techniques, and also hands-on experience with 30+ real projects. You don't just learn concepts, you build a portfolio that companies actually value. You also get the IITM Pravartak certification, Microsoft Azure learning credentials, live masterclasses from IIT Madras faculty, and placement support with AI-powered job assistance. So if you're planning to move into cloud DevOps or even higher paying tech roles, this is one of the strongest programs to get started with, because in today's world, skills matter more than degrees. And this program is built exactly for that. Check the link given in the description box below and in the pinned comments to get a link to this course. Before we move ahead, here's a quick question for you to answer. What does Docker actually solve in real-world development? Is it faster internet speed? Environment differences between deployment and production? Better UI design? Database optimization? Let me know your answers in the comment section below. Now let's dive into Docker and understand how modern applications stay consistent across every environment. Before we even define Docker, let's understand why it even matters. In today's world, applications are no longer simple. They are built with multiple services, databases, APIs, and external tools. And because of this complexity, running an application locally and running it in production often behaves very differently. This is where most of the developers face a common problem. It works on my machine, but it fails on a server. So the real question is not just what is Docker, but why do we need Docker at all? Docker helps solve this exact problem. It makes sure that whatever runs on your laptop will run exactly the same way in any environment, whether it is testing, staging, or even production. So in this module, we are not just learning a tool, we are learning a solution to one of the biggest real-world problems in software development: environment inconsistency. Now let's go ahead a step deeper and understand what was happening before Docker existed. Let's go back to the traditional way of building a software. On one side, we have developer environment. Developers install everything locally: operating systems, libraries, framework, dependencies, configurations. And on the other side, we have the production environment. This is usually different. Different OS, different versions, different security rules. Now here's where the problem starts. Something that works perfectly on a developer's laptop suddenly fails in production. Why does this happen? Because of dependencies mismatch, OS differences, and missing configurations. This situation is famously called as dependency hell. Developers often say it works on my machine, but unfortunately, production doesn't agree. This creates delays, bugs, and frustration in teams. So clearly, we needed a better approach, something that could standardize environments. And that is exactly where containerization comes in. Now, let's understand containerization in a very simple. Containerization is a method where we package an application along with all the dependencies like libraries, configurations, and settings into a single unit. Think of it like a box. Inside that box, everything needed to run the application is already included. So no matter where you open the box, your laptop, a server, or even on a cloud, it behaves the same. This concept is built on OS level virtualization. That means instead of creating, we isolate only the application environment. This makes the applications portable, lightweight, easy to deploy, and even consistent across environments. So instead of fixing environment issues again and again, we simply ship the container. Now let's understand what exactly a container is. A container is a running instance of an image. Let's break that down simply. An image is a blueprint. It contains everything needed for the application, code, dependencies, and even instructions. A container is what happens when the blueprint is executed. So if the image is a class, then the container is an object. Each container runs in isolation. That means it has its own file system, it has its own networking, it also has its own process space. But it still shares the host operating system kernel. This makes containers very lightweight compared to virtual machines. Docker engine is what actually runs these containers and manages them. So now we understand that image is a blueprint, container is a running instance. Next, let's compare containers with virtual machine to understand why Docker is so powerful. This is one of the most important comparisons in the entire module. Virtual machines and containers both help us run application in isolation, but they work very differently. In a virtual machine setup, each application runs with a full guest operating system. It requires a hypervisor, it consumes more CPU memory and storage. This makes it heavy and slower to start. Now compare that with containers. Now, containers shares the host operating system. They do not need a full OS for each applications. This makes them lightweight, faster to start, more resource efficient. So instead of virtualizing hardware like VMs, containers visualize at the OS level. This is why modern cloud systems prefer containers over traditional VMs for most workloads. Now that we understand efficiencies, let's go one level deeper into how Docker achieves this internally. Now let's understand what makes Docker possible at the system level. Docker uses three core Linux features. First is namespace. This provides isolation, so each container thinks it as a running independently. Second is C groups. This control resources like CPU and memory, so one container does not overload the system. Third is union file system. This allows Docker to use layered images efficiently. So changes are stored in layers instead of duplicating everything. Together, these three components make containers isolated, controlled, lightweight. So Docker is not a magic, it's a smart combination of existing OS capabilities wrapped in an easy to use system. Now let's connect with this real DevOps workflow. Now we came to a very important transformation, which is DevOps. Before Docker, development and operation teams worked in silos. Developer wrote code, operation teams deployed it, and in between a lot of issues happened due to the repeat tagging, operations and server. Each step involved manual configuration and this created delays and configuration drift. Now with Docker, this entire flow becomes standardized. We can package the application once they deploy it everywhere. With tools like Docker Compose, we can even define multi-container application in a single file. So the workflow becomes build once, run anywhere, deploy consistently. This is why Docker became a key foundation of modern DevOps pipelines. Now finally, let's understand why Docker is still highly relevant in 2026. Even today, Docker is not just relevant, it is essential. Because we are entering a new era of computing, applications are now evolving into AI system, MCP servers, local LLM deployments, agent-based systems. And all of these require isolated, reproducible environments. Docker helps us achieve that. In fact, over 90% of the enterprises use containers in production. AI workloads are increasingly containerized. Edge computing relies heavily on container runtimes. So Docker is no longer just a developer tool. It has become the foundation of cloud computing, DevOps, AI infrastructure, modern distributed systems. So as we move forward in this course, Docker will be a base layer for everything we build next. In the next module, we will move to the theory to hands-on practice and start building real containers step by step. So first, let's all start with installing Docker. So you need to go to Google and type in Docker. The first link will be from www.docker.com. Just click on it. And when you scroll down, here you will see other options like Docker sandboxes, Docker's AI currents, etc. Now here you have to go for a desktop download. So search for the desktop download and you will find something called as Docker desktops. So when you scroll down, it has a example of how the interface is going to be. It has all the information. It has a Docker engine, Docker CLI, Docker Compose. We have built Kubernetes, etc. All these features are included. And when you come down here, you can see all the development applications with Docker, etc. So now when you come up, you will see an option called download Docker desktop. And according, if yours is a Mac system, go with Mac, else go for Windows. According to your systems, just click on it and it will start downloading. Now after downloading, just double click on the downloaded installer.exe and there with the default options itself, just install it. This will take a few seconds, but it will be done. After that, you'll have a Docker desktop in your Windows. So when you type in Docker, you should be able to find the Docker desktop. Now, when you click on it, initially it will take few minutes or 10 to 15 minutes to start the engine. Since I already have it, it's not a big issue for me to open. But initially, it will ask you the sign-in options and it will always prepare its background. So it will take around 10 to 15 minutes. Apart from this, for coding, we are going to use the PowerShell. So that will be pre-installed in your system. So I'll go to open this. And now the most important settings in Docker when you're working with Docker is connecting it with Ubuntu. So for that, you just need to go to settings and resources here and WSL integration. WSL is nothing but the Ubuntu. So here these two options will be nil. You just enable this and apply the changes and restart your system after this entire process is done. Now there is a very important setting because this will allow you to connect your Docker to the PowerShell and the YSL and the WSL. Now let's check if Docker is installed properly. Now open up your PowerShell and type the following command to verify that the Docker is installed correctly. So you can just type in Docker -- and version, and if it provides you with the proper version, that means it is there. So here the downloaded version is 29.53. This confirms that Docker is installed and accessible from the PowerShell itself. Now let's run our first Docker container. This command in PowerShell to run the hello world container. This is the simplest way to verify that Docker can pull and run a container. So the code for this is Docker run hello world. So there's already a package for the first program in the Docker. So hello world, and if you run it, here you can see hello from Docker. This message shows that your installation appears to be working correctly. This will check whether the Docker can download an image and start container successfully. Now let's run a simple web container. Next, I am starting a web container in detached mode and mapping to the port of 8080 on my local machine itself. Now again, the code for that is Docker run -d -p and the port that you're going to use. Whichever is your local port, you can use it. 8080/80 is also fine. And continue with the name, which is, let's say, welcome Docker, and followed by the welcome to Docker. This is the container. And let's run this. So it is successfully ran. This starts a web app inside a container and publishes it to local host through the port of mapping, which is a core Docker CLI. Now let's check the running containers. To verify that the container is running in PowerShell, this is the container that we have created. Now it should show that this container exists. Now to display all the containers that you have created, just type in docker space ps and press enter. Now this will show you the container that we have created, command created, status, ports which are we using, and the name of it. This lists the active containers and their port mapping. Now let's check if this port actually works. Now go back to Chrome, and since the local host has the welcome, so let's just check. It will be HTTP 080. Sorry, add localhost to that itself, 8080, and enter. So let's correct it. It is HTTP. So let's put it in the host, and can you see here, this is your local host, which is the first container that you have run. This shows the app is running from inside the container, but is accessible on your machine as well. Now, what if you want to remove this container away since it's running and it may interrupt with the other containers? Once everything is done, stop the container and remove it so the environment stays clean. So for stopping the Docker, we have Docker stop and the name of the container. So here it is welcome. So this stops the container. So it has given us, returned us the name. That means it is successful. Now for removing, we have Docker remove rm and the file name, the container name. And when you press enter, it will show you welcome. Now let's execute the Docker PS code again and see if any Docker containers are showing in this list. Now as you can see, there is no containers. We have stopped it and removed it from the Docker itself. This shows the container are temporary and easy to recreate. Now let's move on to images, containers, Dockerfile, Docker Hub. Let's create a app.js in a new folder in your system and obviously give it to change and execute the code that I will execute now. So first let's start with consent of the HTTP, and which will be equal to require of the HTTP. So HTTP and close it. Let's fix that. And next step will be the HTTP dot create. Let's create a server with the requests. So for that we have req, res, and which is equal to or greater than, and then let's put the braces, and then let's open it for res 200, comma, and then open the same braces again. Let's put in a content type also. Let's say it is text or plain, which is basically notebook one. Let's close the curly braces and this one and close it. Next sentence we have res dot end. Let's say hello from my Docker image. And let's close it. This is what it's going to print. And later we have braces closed, which is the previous braces closed, dot listing. So listen and 3000. And let's just close it. This is a very small node.js app that will package into a Docker image. Now let's create a Docker file. This file will tell us how to build the image. Now this is the image itself. So let's just save this, and in the same file, you can just create another text document and then change it, open it, and give like what are the steps in JavaScript, how are you planning to execute this, or which app or which installation process should go on. So we have from node, leave a space, node, which node are we targeting now? 20, and let's put Alpine, and we have work dir /app. Let's also copy JS and also expose. We are setting it to 3000. And then finally we have CMD, which is node. Let's put double quotes, comma. We have app.js. Now here the Docker file defines the base image, working directory, copied files, exposed port, and also startup command docs docker. Now let's build the image. Open the PowerShell, move into a project folder. So just copy the location from here and go back to PowerShell and direct it, cd space the same location, and enter. Okay, there is some. So if this is showing that the location is not set, so let's set the location, and here we are into the folder. Then we'll run docker/d. Sorry, it is docker build t. Docker build -t. Let's add some more information on that. Let's say docker build /t my node demo. So let's just set the location as per that. So we have set location again. So I don't want to execute this. Instead, I want to set the location back. So we have set location, and let's put the path and give. After, even if you rename your folder, you need to do it again. So go back, copy the name, and come back here and set the location and close it. First, let's run the cd first, and then let's set the location. So it's already showing us, but for our safety, we can just set the location back again. So again, just set the location and run it to make sure that your same console we have. Now, as we talked before, we want a build.function. So what was the command that I gave earlier? Just print in docker build t my node demo v1. So, and enter it. And this will take some time. It's showing us failure. Now, if you get any error, make use of AI, ChatGPT, Perplexity, or any other tool. Just take a screenshot and put it to the system and ask what is the error and continue your coding. So here the error was if your file is not exactly Docker file, which is D caps F caps, it might read a wrong file. So here if you give /f, it will take in any kind of Docker file as well. So let's give that. So as you can see, it will start building, and fail to build, fail to solve, fail to read the Docker file. Open Docker file, no such files or directory. Let's sort this out first. Now, in order to run this code, make sure you have the exact Docker file without any extension. So I had .text which couldn't read. So delete that .text and let's have the same Docker file as the name. So here this packages the applications as a reusable Docker image. Now let's check the local images as well. To confirm that the images was built successfully, list the available Docker images. For that, just type in Docker images. So we have Docker and images. As you can see, we have a couple of them. This shows the new custom image is in the local image list. Now let's run a custom image as a container. Run the image and map port to 3000 on the host to the port 3000 inside the container. Now how do you do this? Again, it's a simple code. Let's say docker run d, and let's put in p and also the port to be hosted with the containers port to be hosted. Here both I'm taking it as 3000 itself. Then let's name it name. Let's say my node, and let's give the image also. So it will be my node, and let's give it demo. Let's say this is v1. So let's give this. This starts running container from the custom built image. Now open the browser and verify that the custom app is running. Now again, go back to the previous local host that we have hosted. So here the local host is 880. So the host that I did was 3000. So can you see hello from my Docker image? That's the output. This confirms that the custom image is working correctly as a container. Now let's view the logs. To confirm the container started properly, check the logs. So by the way, while you are running every single code, everything will be in this Docker itself stored. So let's go back. And here you will see the entire log of what are the codes, if you're fetching the data, if you're fetching with the time as well. So you can cross check if actually the code is working from here. Obviously you'll get the output, but still. So for checking the logs, we have Docker logs, my node, and enter. Logs help verify container startup and are useful for troubleshooting. So as you can see, it has executed successfully. Now let's clean up. Stop and remove the container after verifying. So again, what is the step? We have to stop it and then remove it. So we have Docker stop and the name. What was the name? My node. And then next we have Docker remove, which is rm, and my node. And that will be successfully done. This resets the environment for the next part of the demo. Now let's talk about volumes, bind mounts, persistence. Let's create a Docker volume. Type the following command in PowerShell to create a named volume for persistent storage. So for creating it, we use Docker volume create Mongo data. Now this will create Docker managed persistent storage. Now let's run the MongoDB with the volume attached. Run the MongoDB container and mount the named volume to the database data directory. So for that, you say Docker run in the directory, and let's name it. Let's say Mongo. Demo is the name of it. And let's say in PowerShell, we have a certain port. So it is 27017 and 27017. This is the port I am selecting, and then we have v Mongo data. Use the isto and slash. What we are extracting the data and database Mongo. This will be the code, and run it. This stores MongoDB data in the named volume instead of the container. Now let's verify the volume. So this will take a few seconds to be done. Now after it's done, to confirm that the volume exists, list all the Docker volumes. Now how do you list all the Docker volumes? So we say Docker volume and ls. Sorry, it is L in small and S in small and enter. Now can you see we have Mongo data which is local and the host name is also here. It is created. This shows the named volume is stored independently of the container. Now let's recreate the container using the same volume. Stop and remove the container, then start a new one with the same volume. Again, how to stop the container? We have Docker stop and the name. What was the name? Mongo demo. And then followed by again Docker stop. Instead of stop we have remove, which is rm, and it's done. Now let's run the docker / name. So again we are trying to run the Mongo demo without the volume. So let's see if it throws an error. Demo 2. We are creating a new one as of now, and let's give the port name as the same 27017, and again 27017/v, and again Mongo data, and let's give a slash and obviously data and database Mongo. So let's run this, and as you can see we'll create another volume. This demonstrates persistence beyond the container lifecycle. Now let's demonstrate a bit mount. Create a local folder with an index.html file, then mount that folder into the nginx container. Now how do you do this? Again, docker run d name and the kind of file that we want, which is nginx bid and the port name followed by the code. So here you can take docker run /d and the name we are giving, and again PowerShell, and then we are giving the port name. Here let's consider 8081/8081, and then v, and let's run it. So there was an issue, so let's check with repeat. So again, if you get any error, check with the AI tools that you are having. So here I am giving the Docker course demo for etc. all the other information that I've given earlier, and then pressing enter. It's showing unable to find the image, but still it is running. This maps a Windows folder directly into the container, which is ideal for local development and also file editing. Docker Desktop on Windows supports volume mounting and localhost access for this workflow. .docs.docker. Now let's verify the bid mount. Open the browser and refresh the page after editing the HTML file locally. So here the local host was used as 8081. So let's check what's happening. It's not found because we have not added any image, because here the first error was unable to find the image, this one latest. So let's rebuild that. So I found another code which will get the image and then execute it. So let's execute it, and I think it is done. Let's check with the local host. Let's refresh it. It's 8081 itself. Nope, it's still an error. Again, just go back. So let's again, I have just given the screenshot of the same error to either Perplexity, ChatGPT, whichever model works for you, and they'll give an alternative option, and you will learn your mistakes as well. Make sure you adopt it throughout this entire course. Now let's refresh the local host. I fixed my error and let's see, host 8081 and still it is showing the same. Let's try once more. Okay, we forgot to create a HTML file basically. So let's create a new folder. So I'm just creating it here itself. New folder. And let's say demo4. And inside that I want index.html file. So new text document and let's say index and HTML and copy this address, open the HTML file and give it a code HTML. So let's put it to text back and give a code where it will show us, say hello from Docker, and then save it, close it and go back to your PowerShell. Let's execute the same code with the same amount of location that we have used and let's see what's the result. I've just changed the location. I realized that there was no HTML file. I've again gone and created a HTML file, changed the location of the HTML file as well. Now let's look at the page. Localhost 80, sorry, and it's still showing 403 forbidden. So we need to figure out what was wrong. Okay, I got to know the error. The error was basically this is index.text, which I have not changed back to HTML. So let's give that and give it yes and go back and run the same code. Again, it's the same code, so I've just copied and pasted it and enter. And now hopefully you will be able to see the right page. So let's reload it and still it is 404. So let's, I don't know. Now I will change the port to 82 because 80 is already preoccupied. So let's see how that goes and let's check. And here you go, we have the file. So if you have any issues with your code, please make sure to tell it to any other AI tools. It will give you a probable where are you going wrong and then you can fix it. For here it showed me that 8081 is probably occupied in some other code running, which is fine. Now change it to 8082. Now I did it and immediately I got the output, which is hello from Docker. This shows local file changes are reflected immediately inside the running container. Now we are moving into one of the most important concepts in Docker, which is networking and ports. Until now, we have seen how containers are created and run. But in real application, containers never work alone. They need to communicate with other containers, with databases, with external users and systems. So in this module, we will understand how Docker manages communication between containers in a secure and controlled way. Let's start by understanding why networking is actually needed in a container system. In traditional application, everything used to run on a single server, but now modern systems are broken into multiple services. For example, web app container handles UI request, API servers containers handles logic, database containers stores data. Each of these runs separately. So the question is, how do they talk to each other? This is where networking becomes critical. Docker provides isolated networking for each container, meaning containers cannot randomly access each other. Communication happens only through defined rules. This gives both security because everything is isolated and control because communication is international. And most importantly, containers can safely exchange data in a structured way. Now let's understand how Docker actually creates this networking system. Docker provides different types of network drives depending on the use cases. Let's understand three most important ones. The first one is bridge network. This is the default. It is used when containers need to talk inside the same host system. Second is host network. Here the container directly uses the host machine's network. This removes isolation, so it is faster but less secure. Third one is non-network, which is also called as zero network. In this module, container has no network access at all. This is used for very secure or offline workloads. So depending on requirements, Docker gives us flexibility, default isolation, which is the bridge option, high performance, which is the host option, and full isolation, which is the none option. Now let's go deeper into most commonly used one, which is the bridge network. The bridge network is the default networking mode of Docker. Think of it like a private internal switch inside your machine. When containers are created, Docker assigns them internal IP address like 172 point some number. So containers inside the same bridge network can talk to each other using these internal IPIs. We can also create custom bridge networks to isolate applications for each other. For example, one network for front-end, back-end, another network for database services. This helps in better security, better organization, controlled communication. Docker also provides DNS-based discovery inside bridge networks. This means containers can talk using names instead of IP addresses. Now let's understand how external users access containers through ports and mapping. Now, this is one of the most practical concepts in Docker. By default, containers are isolated and not accessible from outside. So, if a web application runs inside the container, how does a user access it? That is where port mapping comes in. Port mapping connects host machine port, container port, for example, localhost 8080, container is 80. So when a user opens browser and hits a URL, the request is forwarded to the connect container port. We can define this using docker run p. Host port, container port, we can also expose or even publish ports depending on visibility needs. This allows a secure access control, external communication, controlled exposure of services. Now that we know how external communication works, let's see how containers talk to each other internally. In modern applications, servers are always split. For example, web container, API container, database container. Instead of exposing everything externally, they communicate inside a private Docker network. So the flow becomes web container, API container, database container. This communication is private, secure, and fast. Docker uses internal DNS resolution, so containers can simply use service names instead of IP addresses. For example, instead of calling 172.18.0.2, we can just call DB. This makes architecture clean and scalable. Now let's combine everything into a real system design. Now we are entering real-world architecture design. A modern application is never a single container. It is usually includes front-end or web proxy, back-end API, and databases. In this architecture, each component runs in its own container, but all of them are connected through a private Docker network. We also introduce concepts like load balancing using proxy layers, separate backend and database communication, secure internal networking. This is how real production systems are built in companies. The key here is each container has one responsibility and networking connects them together. Now, finally, let's see how all of this becomes easier using Docker Compose. Until now, we have manually understood how containers connects, but in real projects, managing multiple containers manually is difficult. That is why we use Docker Compose. Docker Compose allows us to define multiple containers, networks, volumes, and even dependencies, all in a single YAML file. So instead of running multiple Docker run commands, we simply run Docker Compose up. This brings simplicity, automation, repeatability. So in this module is very simple. So this module is very important because networking plus Compose is what makes Docker production ready. In the next module, we will go deeper into Docker Compose and start building multi-container applications step by step. Now let's move on to Compose YAML scaling environments. Let's create the application file. Create a file named app.js and paste the following code. Now again, I've taken AI tools help and got the code. So let's go through the code once and then let's proceed. So let's say we have demo 6 and I'm creating a new text, say let it be app.js. Open it and paste the code according to whatever your demo is. So let's just paste it and I'll explain you what this code does. So again, it's similar to the previous app.js file. It's just that the port has been changed. It's the same one actually. It is literally copy and pasted of the before one. Now this app reads environment variables and display the Redis host name. Now let's create the Dockerfile. Again, similarly to the first demo, let's create a Dockerfile in the same folder. New text document. Let's say Dockerfile. Open it and paste the code. Again, this will show how to run the containers. So again, it's a similar one as of to the before one. So control save. And one more thing that we last time missed out on was, while the Docker file is there, we forgot to take out the .txt. Let's remove that as of now. And yes, this packages the app as a Docker image. Now let's create the compose file. Create a file named compose.yaml. This will define both the app services and Redis. So we need another file. We'll rename it later. Now let's just open the YAML file and build the things. Now here I have services, app, build ports, which is environment port, etc. given. So control save, and then you have to rename it. Make sure to rename it. So here we have compose.ml and enter. And obviously it will ask you whether you really want to change it, and we'll give it yes. Now this defines a multi-container application in one YAML file, including services, ports and environment variables .docs, which is a Docker plus one. Now let's start the compose application. Open the PowerShell and go to the project folder and bring up the full application stack. Now here again the code, it will be almost the same except the location and the file name will change according to your preference. I would suggest keep the file name at least the same, since the location can be anywhere. Copy the location and replace it with the location that you are currently using it. And after that, after this code, this builds and starts all services from the compose file. Docker Compose is designed to define and run multi-container applications with a single command .docs.docker. Now let's verify the services. Again, this will take a few seconds to be done. Now actually let's confirm the services. To see all the running services in the application stack, type the following command. So it will be docker compose ps. So as you can see the service, which is Redis 1. This shows the running compose services. Now let's open the application. Open the browser and verify that the app is running and reading the Redis host value. So the host will be in 3001. So let's change the port and enter. So I think the major issue with this is the port number. So let's just change it. So let's give, instead of 3001, let's give it back to 3000, since that was an output one. So here, let's save it and go back and execute the same code. So again, it might take some time, but I think it will create. Now let's take a look at the compose ps, where all the containers will be there, and it is showing me it is there, but it is created 4 minutes ago. So let's check if this actually works. No, there is some issue with the site itself, localhost or something like that. So anyways, let me know in the comment section below what output did you get. I don't think so you will have much problems with ports. My ports are being regularly used. That's why it's showing an error. So in this step, this will confirm the app services is running from the compose stack. Now let's scale up the app services. Now next step, you can give it compose up to D scale app 02, meaning this demonstration simple services scaling in Docker Compose, Docs. Now again, if you want to bring this down, which is the compose down, there is a code for it. So let's bring this Docker down. So here we have Docker compose and let's just type in down. So it removes it and it has removed successfully. This removes the running services created by compose. Now we are entering one of the most important parts of Docker, which is security. Because in real world systems, it is not enough to just run containers. Make sure that they are safe from attacks, properly isolated, properly configured, and protected from data leaks. Security is not a single feature in Docker. It is a combination of multiple layers working together. So in this module, we will understand how to secure containers from the ground up, starting from architecture to runtime safely. Let's begin with why security actually matters in container system. In traditional systems, security was mostly at a server level, but in container systems, things are different. All containers share the same host operating system kernel. This means if one container is compromised, there is a potential risk to entire system. That is why we say containers have a shared kernel model, and this increases the importance of security. Now think about real world issue. Misconfigured containers running with too many permissions, insecure network sockets exposed, poor image configurations. These are common entry points for attackers. So we follow one key principle here: defense in depth. This means we don't rely on one security layer. Instead, we secure every layer from image creation to runtime execution. Now let's start with one of the most important decisions in container security, which is root or non-root execution. This is a very critical concept. By default, containers can run as a root user. But this is dangerous because if an attacker gets access to the root container, they can potentially gain control over the system. So the safer approach is to use a non-root execution. Let's compare both, which is root execution, which has full privileges inside the container, higher risk if compromised, not recommended for production. Non-root execution has limited permissions, safer environment, recommended best practice. In simple terms, never give more power than needed. This principle alone can prevent many security issues in real-world deployments. Now let's move to the file level. Security inside the containers. Now we are looking at how data inside containers is protected. One of the best practices is using read-only file system. This means the application can run, but it cannot modify core files. Because if a container is compromised, the attacker cannot change system files or inject malicious code easily. We also use temporary file system for runtime data, strict volume permission for external storage. This ensures control, write access, protection of static application files, reduced attack surface. In simple terms, only allow writing where absolutely necessary. Now let's talk about secret management, one of the most sensitive areas in Docker. This is where many real-world applications make mistakes. Applications need sensitive data like API keys, passwords, database credentials, SSL certificates. A bad practice is using environment variables for secrets. Why? Because environment variables can be exposed in logs, debugging tool, and container inspection. Instead, Docker provides a secure way called Docker secrets. Secrets are stored securely, mounted at runtime, never returned into images or logs, so comparison is easy. Environment variables, easy but insecure. Docker secrets, secure and production ready. So the rule is never hard code secrets insert image or code. Now let's move to another important concept, image vulnerability scanning. When we build Docker images, we often include libraries and dependencies. But what if one of those libraries has security vulnerabilities? This is where scanning becomes important. Docker and other tools help us scan dependencies for known CVEs, detect vulnerabilities before deployment, block insecure images in CI/CD pipelines. This can happen at different stages during build, before pushing to registry, or even before deployment. And before deployment, we also follow standard tools like Triv, Grape, Docker Scott. So the idea is very simple. Do not trust an image until it is scanned and verified. Now let's combine everything into a full security strategy. This slide will bring everything together into a complete security model. We don't just secure containers with just one method. We follow 5-pillar technology. First one is minimal base image. Use only required dependencies. Second is run as root node, reduce privilege level. Third one is limit resource, prevent resources abuse or even attacks. Fourth is layer scanning, which is scan images at every stage. The fifth one is protect secrets, never expose sensitive data. When you combine all these, you create a hardened container system. So instead of thinking security as a feature, we treat it like a design principle. Security is not added at the end, it is built from the beginning. Now we are entering into a very important stage of Docker learning, which is orchestration. Until now, we learned how to create containers, connect them, secure them, and manage networking. But in real production systems, we don't just run one or two containers. We run hundreds of containers across multiple machines with automatic scaling and recovery. So the question becomes, how do we manage containers at a scale? That is where containers orchestration comes in. And in this module, we will compare two major orchestration tools, which is Docker Swarm and Kubernetes. Let's start by understanding why orchestration is needed in the first place. Earlier, we used to run applications on a single machine, but now modern systems are distributed. We have multiple nodes working together in a cluster. At the center of the system is a control panel, which manages all the nodes. Now, why do we need this? Because modern applications require high availability, load balancing, self-healing when something fails. For example, if one container crashes, the system should automatically restart it. If traffic increases, the system should automatically scale. This is what orchestration solves. Now let's understand why orchestration is usually needed in real systems. Without orchestration, we faced the first thing is single host limitation. If one machine fails, the entire application goes down. Second thing is manual scaling. We have to manually increase or decrease containers. Third one is downtime risk. Any failure requires human intervention. Now with orchestration, everything changes. We get intelligent load balancing, automatic scaling, self-healing systems. So instead of manually managing containers, the system manages itself. This is the foundation of modern cloud-native architecture. Now let's understand Docker Swarm, the simpler orchestration tool. Docker Swarm is a Docker's native orchestration tool. It is built directly into the Docker, so it is very easy to use. Its biggest advantage is simplicity. You can turn multiple Docker machines into a single cluster using just few commands. Swarm gives Swan gives us easy setup, fast building curve, built-in clustering, but Swan is mainly used for small to medium workloads. It is simple but not very powerful for a large-scale enterprise system. Now let's move into Kubernetes, the industry standard. Kubernetes is one of the most widely used container orchestration platform in the world. It is originally built by Google and now is maintained by CNCF. Unlike Swans, Kubernetes is more powerful, more flexible, and also more scalable. It introduced a control panel that manages scheduling, scaling, and deployment self-healing. In Kubernetes, everything is declarative. That means we define what we want and Kubernetes make it happen. This makes it ideal for enterprise applications, microservice systems, large-scale cloud platforms. Now let's compare Swarm and Kubernetes directly. Docker Swarm is easy to set up, fast to learn, good for simple application, best for small teams and prototypes. Kubernetes is more complex, requires more setup, but extremely powerful, used in production at massive scale. So the trade-off is simple. Swans gives us simplicity, Kubernetes gives powerful and scalability. In real-world companies, Kubernetes is a preferred choice for enterprise-grade systems. Now let's go deeper into the Kubernetes architecture. Now we need to understand how Kubernetes actually work internally. There are four main concepts. The first one is pod. This is the smallest unit in Kubernetes. It can contain one or more containers. Second is node. This is a machine where pods run. Third is deployment. This manages how applications are deployed and updated. Fourth is services. This exposes applications to internal or external users. All of these are managed under a cluster. So Kubernetes is basically a system that organizes containers into a structured units and manages them automatically. Now let's understand how deployment actually happens step by step. It starts with a container image. We create the container image. Step 2 is to we define a pod manifest using YAML. Step 3 is the deployment controller manages scaling and updates. Step 4 is a service gateway exposes the application. Step 5 and finally uses access the application. The key idea here is everything is declarative, not manual. So instead of running commands repeatedly, we define configuration files and Kubernetes handles the rest. This is what makes Kubernetes powerful in real production systems. Now we are moving from container orchestration into a real-world cloud deployment patterns. Now let's talk about Docker and CI/CD automated testing. Let's create the application logic. Create a file named sum.js and paste the following code. So now let's create sum.js. It's a JavaScript program. So text document. So it is sum.js and give it yes and open the file and type the code. So basically we need to write a code where we are giving a function of sum a comma b and we are returning the additional value of it, which is a plus b. So let's say it is function sum, which is a comma b, that is the inputs that we are giving in, and let's say return. What are the value that you have to return? The sum of them, no? So it is a plus b and hyphen. So there is an error in the spelling here, and yeah, now you can save it and close it. Now this is a tiny function we will test inside a container. Now let's create a test file. Create a file named test.js and paste the following code as well. So again, we want a new text document and it is test.js and delete the rest and enter. Yes, we want to change it and open it. And here again, what happens is we have to have the construct call the function is equal to require. Again, you can use ChatGPT to get the code of whatever kind of program you're wanting. And then we have if sum, we are passing values here 2, 3. So the value of return should be 5 is not equal to 5. That means if it is an error, then we need to throw the new error, which is test failed. So it is throw new error, which means the function is not working properly. Throw error and test failed. And let's close this. And then let's say console.log. Let's say test passed. If the value is returning the accurate amount, let's say the test is passed. And let's close it. So for these, let's just save it and close it. This state validates the logic and exists with success or failure. Now let's create a Dockerfile. So again, you know the procedure of creating a Dockerfile, right? So just open it and paste the code, give it conditions to how the code should work. Now here again I have given from node 20 Alpine, worked their app, copy sum.js, test.js, and then we are testing it. So save it and then change the name of the file, which is Dockerfile without any extensions. And give it yes and you'll be set. Here this will create a test container that executes automatically. Now let's build the test image. Open your PowerShell, move into a project folder and build the image. So again, the first step will be to relocate. We have CD and the location given and enter, and successfully we are in the demo 9 folder where all the folders are present. Now you guys already would have guessed the next code, which is to build a test demo. So let's give that and press enter. Now let's run the test container and also let the test execute automatically. So here to execute the code, we have Docker, again what run, and rm test. We are testing demo in v1 and enter. Okay, there is a small typo issue in this. So let's fix that quickly. So I've a little bit changed the code so that it understands. So let's just save it and run the code. And let's see what happens. Again, there's an issue. Okay. Let's build it from first and then let's give the folder. Let's test it. And there are no issues as of now. This simulates how CL systems run automated tests inside the containers. So since we don't have any output such as wrong outputs or mispronounced or any other things, the system is running fine, the function is running fine. You can also give a code in such a way that if it's run properly, you will get the output as well. Let's move on to logs, matrices, and troubleshooting observability stack. Let's start with a simple container for troubleshooting. Open a PowerShell and start a basic nginx container that we can inspect. So since we have already created one and again recovered, we'll just directly move into the theory part. So I'm here creating it. This gives us a simple running container for observability checks. Now let's generate some more traffic. Open the browser a few times so the container creates log entries. So the browser will be 8083. So let's go for 8083. And as you can see, we have here. Now let's open this and close this multiple times so you can create some traffic. So 1, I'll open another Windows. 2, let's close the other window, again open it. And can you see there is no delay also, it's too quick. So again, let me just create it and observe the time as well that you are creating. This creates activity, we can observe it in the logs. Now check the logs. To view the runtime output from the container, type the following command on the PowerShell. So here we have docker logs obs demo. This shows the container logs which are core troubleshooting sources. Now let's check the resource usage as well. To see a CPU and memory usage for the running container, run this command, which is docker stats no stream. Let's put double slash and then no stream. Now this will show a quick resource snapshot for activity containers. So as you can see, we have CPU, name, the limit, the mem percentage, and ID, block ID, etc. Now let's inspect the container configuration. To view a detailed metadata such as port configuration, use inspect. So for that, let's say docker inspect obs demo. This will show low-level container details. Now let's open a shell inside the container. To inspect the container, intentionally open an interactive shell. For that, you need to just type in docker space it space slash obs. What's the name? Demo. And let's take out this because it's not required. And lastly, we have sh. Now this lets you inspect files and process from inside the running container. This will take a little bit of time. Now after this, if you want to stop and remove the container after troubleshooting demo is completed, then you can use docker stop obs demo, and then you can remove it by similarly docker rm obs demo. This resets the environment. Now we are at the final stage of the Docker journey. In previous modules, we learned everything from basics to advanced orchestration and security. Now in this final module, we are not learning new concept. Instead, we are learning how professionals actually use Docker in real production systems through best practices, common mistakes, and industry standards. This is the module that separates a learner from a job-ready engineer. So let's begin with how Docker is used safely in production environments. Let's start with the production best practices. When companies move application into productions, they don't just focus on making things work. They focus on making things efficient, secure, scalable. First best practice is using small images. Smaller images are faster to build, faster to deploy, and have fewer vulnerabilities. Second is multi-stage builds. This helps separate build environments from runtime environments so final images stay clean and lightweight. Third is using Docker ignore files. This prevents unnecessary files from entering the image, which improves security and performance. Fourth is using immutable tags. Instead of using latest, we also use versionized tags so deployments are predictable. So the main idea is simple. Clean, minimal, and controlled images are always win in production. Now let's move on to common mistake developers make. Let's talk about the mistakes, because in real world systems, mistakes cause failures more than complexity. The first one is mistake is running containers as root. This is dangerous because if container is compromised, the attackers get high level access. Second mistake is using large bloated images. This slows down deployment and increase attack surfaces. Third is mistake hard coding secrets inside images. This is one of the biggest security risks in production system. Fourth mistake is ignoring logs. Without logs, debugging becomes extremely difficult in distributed systems. So the key learning here is most Docker issues are not technical problems, they are configuration problems. Now let's go one level deeper into the system design thinking. Now we are not just talking about Docker anymore, we are talking about the future of container systems. Containerization is evolving into new areas. First is AI agent sandboxing. Containers are now used to safely run AI models and agent systems in isolation. Second is edge computing. Lightweight containers are deployed on devices closest to users for faster responses. Third is WebAssembly integration. This allows ultra-fast execution environments alongside containers. Fourth is zero trust architecture. Every container is verified, monitored, and secured continuously. So Docker is no longer just a packaging tool. It is becoming a foundation for modern distributed computing systems. Now let's understand how container expertise fits into real careers. Now let's connect Docker skills to real careers. Container expertise is not limited to one role. It is required in multiple roles like full stack developer, DevOps engineer, cloud solution architect, site reliability engineer, platform engineer. As we move higher in the list, the complexity increases. At the top level, we have platform engineers and SREs, which is container knowledge becomes critical for building scalable systems. So the key message is Docker is not just a tool, it is a foundational skills across modern tech roles. Now let's look at the resources that help you continue learning. This slide shows you your learning journey. It starts with core Docker fundamentals, then move into Kubernetes orchestration, then CI/CD automation, then infrastructure as code, and finally observability. This is real progression of cloud engineer. Each stage builds on a previous one. So instead of learning random tools, you should always follow a structured path. Now let's understand what resources you should use to grow further. To become industry-ready, tools alone is not enough. You also need strong learning resources and certifications. Start with official Docker documentation. It is always the most reliable source. Then practice using interactive labs and sandboxes. Explore GitHub repositories like Awesome Docker for real-world examples, real foundational books to understand deep system concepts, and finally, certifications like Docker Certified Association, Kubernetes, CKA, AWS DevOps certification. These validate your skills in the industry. So the idea is simple: learn, practice, and validate your skills continuously. Now let's close this entire course with a final message. If you have reached this point, you have completed a full journey from understanding containers to networking to security to orchestration and finally to real world best practices. You're no longer just learning Docker, you're now thinking like a cloud engineer. But remember, tools will always evolve. Docker today may change tomorrow, but the concept you learned here, which is isolation, scalability, security, and orchestration, will always stay relevant. So keep building, keep experimenting, and most importantly, keep learning by doing. This is just the beginning of your cloud native journey. So now you have gone through the fundamentals of Docker and containerization. You started with a real problem. Why does my application work on my system but fail in production? And now you understand the solution, which is containers, isolation, standardized environments, Docker-based workflows. But remember, this is just the beginning. Docker is a foundation of modern technologies like Kubernetes, CI/CD pipelines, microservices, cloud-native systems. If you found this video useful, like this video, subscribe to Simplilearn, and continue to the next module of deeper Docker concepts. Until next time, thank you for watching and stay tuned for more from Simplilearn.